I'm going to be talking about using and understanding deep neural nets. The understanding is going to be really trying to just understand a tiny little bit. We're still a long ways from really understanding these things. But the goal is for this to be a very practical tutorial where I hope that you can, at the end of the day, be able to start using these tools for whatever problems you have, because we're at a really nice time right now where there's very good code implementations of deep learning, and they're very easy to use, and they're much simpler than they ever have been before. Okay. So by the way, if you ever have any questions, you can stop me, raise your hand. This can be totally interactive, so just if anything is unclear, feel free to ask questions. So as you guys know, the brain is a neural network, and this has led to a lot of, this has been kind of a motivating principle behind the development of these architectures for understanding the brain and also for making artificial systems. And the kind of classical picture that's been developed over many years is that the brain takes some input, some visual input, and processes it through a hierarchical series of simple computations. So first, maybe you take that box and you extract edges, and then you figure out some surfaces as you move up from V1 to V4 and V3 and et cetera. And then you get up to IT and you start doing object recognition, and then maybe you go off beyond that into memory and cognition. So this picture is really what people have been able to make progress on in actual artificial systems. So we're going to try to understand those artificial implementations of this kind of hierarchy. Because my background is vision, I'm going to mostly be talking about examples in vision. But for many of the examples, you can just replace the visual input with a spectrogram if you want, or with a sentence, and everything would work basically the same. So we're really going to be looking at what are known as convolutional neural nets here for the most part, but the principles and architectures are quite similar for, as you guys heard last week, RNNs, recurrent neural networks. These things are all fairly minor variations on one theme. Okay, and the reason why this is really exciting right now is because in 2012, and around then, there were several papers that came out that suddenly showed that computer vision and speech recognition and these things actually work. So this was a very popular paper in making everybody get excited about deep learning. This was Alex Kravetsky's paper from 2012. And what I'm showing here is some images that the system has never seen before. And using a deep learning architecture, it's learned how to recognize all of these different objects. So it's learned that that leopard can be labeled automatically as a leopard. So the top row in each of these columns here is showing the label inferred by the network, and it's often correct. So it can recognize squirrel monkey and Dalmatian, and this is kind of magic, that it suddenly started working really well, and it suddenly started working much better than what had come before. Okay, so just a couple more fun examples to show how powerful and amazing and magical these techniques are right now. So a very recent line of work has been on taking an image and producing a sentence automatically. The system is trained to map images to sentences, and it can produce pretty compelling results some of the time, like here's a pot of broccoli, and it says a pot of broccoli on a stove. Okay, and then two more examples are, maybe you've heard of some of this for image recognition, that deep learning is really powerful, but you can solve many other problems this way. So whenever you have some input and some output and you want to find a mapping between them, these architectures on all kinds of problems are getting really nice results. So you can take an image in and get out a spatially varying map of labels or of shape descriptors like surface normals or a depth map. And you can do this on other domains as well, although I'll be mostly talking about vision. So you could do it in speech, where you're able to generate human-like speech with a network where it tries to map text to an auditory waveform. Okay. So in this tutorial, what we're going to do is the first hour or so will be me going through the basics of how these things work. a little bit of insight, I hope, into what they learn, and then practical use, how to actually start coding these, how to actually start using them for your research. And then the second half of this tutorial is going to be you guys will work through the exercises. Joseph and I will be here to help you with them, and hopefully we can all kind of together work through some of the exercises, and then additionally you can take those home and continue to work on them. Okay. Okay, so how do these work? The basic idea is really simple. We have some image or some data in. We have then a brain neural network, or now a machine neural network, and we want to output some information about that thing. So the classic one is just image recognition. So we take a clownfish, and we have a system that can learn to tell us it's a clownfish. Okay, so what people have done to solve this problem in the past is, this comes from the kind of David Marr's hierarchy of how the visual system might work. It comes from intuition from neuroscientists about how V1 extracts edges, and then V4 extracts surfaces, and so forth. So first what you do is you build a lot of systems. If you want to solve this problem automatically, you take the clownfish, and you run an edge detector. And maybe you run a texture descriptor called, one example is called textons. This is just describing the kind of texture information in the image. Maybe you extract some description of the colors. You say it's blue and orange and white. Okay, so then you move up to the next layer. You move up to like a V4 type representation. You get segments. You try to mark where the fish is and where the water is. Maybe you get parts. You try to recognize a fin or an eyeball. And eventually you put it all together into a label. And people have traditionally thought of this as first you design these hand-engineered feature extractors that try to identify important parts of the input, and then you have a learned classifier at the end which takes all those features and decides what they mean. And they say that this is a clownfish. Okay, so people did this in a whole lot of domains. For example, in speech recognition, or this is, I guess, an example of music recognition. You can take an auditory waveform, you extract some features like a spectrogram. You maybe start to group those together into a hierarchy of more and more complex structures, representations. Like you get notes out, and then you put a classifier in the end, and it says box cello, suite number 1. And in a fairly different domain, you can take a sentence in, you extract some words, you have some engineered systems that will try to compute n-grams and map that onto meaning, and eventually you map it back to maybe a sentence in Chinese saying the same thing. And so all of these systems have traditionally worked by a lot of engineers kind of replicating brain-like processes for the first couple steps, and then adding a machine-learned classifier which just tries to take all of these, this engineered representation and learn how to map that onto a label clownfish. So you're only learning the very final set of arrows. And the basic idea of deep learning is that let's not engineer anything by hand. Let's learn all the arrows. And the boxes now are not going to be explicitly an edge extractor or a part descriptor. Instead, it's just going to be some generic unit that will be learned. And this is a really old idea. So for many years, people worked in the 80s and 70s even on systems like this. They take something in, and they have a neural network architecture, which is a couple layers of processing units that try to predict a label. And then the recent thing has been deep learning just means, OK, put more of those together. But the architectures and the algorithms are really similar to what came out in the 80s and the 90s. OK, so we're specifically going to be talking about a type of neural net, which is a convolutional neural net. So the way these work is the unitary operations in the network are convolutional filters. So to show you guys what that means is you have some kind of filter, like a Gabor filter, which is just, this is going to be something that you will slide over the image and calculate the dot product of that filter with the image content. So you're just going to take that filter, you're going to swing it all over this image, and it will produce an output, which is how much that template, that filter, matches the underlying image content. So it's kind of looking for that type of structure. This filter is looking for these light-dark patterns. So this is basically looking for edges, and you get an output like this. OK, so these networks are going to just be doing a lot of computations, which are these kind of convolutional filters. And this is very similar to what we think might be going on in places like the visual cortex, where Hubel and Wiesel identified that V1 seems to have Gabor-like filters. It scans across an image to detect things like edges. OK. So just to make it even more explicit, what we're going to be doing is taking an input representation, which might be an image, and we're going to be passing these computational units, which are just local and translationally invariant filters across the image to produce some output in a set of feature channels. We're just going to be stacking these on top of each other. But let's look in a little bit more detail at the exact computations that go on in kind of the standard current set of models, the current state-of-the-art popular models. There's a whole bunch of models that we could play with, but I'm going to only be telling you about the ones that are most popular right now and actually really effective. OK, so the basic computation is you have a stack of simple repeated units. And for a single computational unit, it's just going to take an input representation, maybe an image, or maybe a mid-layer of the network. And it's going to produce an output representation. And so how does that work? So it's modeled off of the idea of neurons that are connected by edges. So you have to produce an output at some particular node, so some particular feature in this output representation. It's going to look at all of the inputs and take a weighted combination of them. It's just going to be a linear operator. And we're going to do this for every single node in the output. I'm only showing one for simplicity. But every node can potentially be connected to every other node. And the fundamental computation is really simple. It's just a weighted average. It's just a linear combination of the input. So if the input's pixels, you're just going to take a weighted average and produce some output representation. And in convolutional networks, this weighted average is going to be a convolutional filter, which is just you slide it across the image. OK, so that's the first step. You just do a filtering operation to try to take some aspect of the input domain and select it out, filter it out of that representation, like, for example, detect an edge. OK, so we could just start stacking these up, but that wouldn't be quite enough because this is just a linear operation. If you concatenate multiple linear operations, you still get a linear operation in the end. And you don't get any better abstraction or representational capacity. So in order to actually perform more nonlinear computations, the next thing that people add, the next ingredient, is a pointwise nonlinearity. So what this means is that you take your input x, you do a linear combination to get your next level representation y, and then you take that representation and you pass every single node in that representation through a pointwise nonlinearity. And the popular one right now is this thing called a rectified linear unit. This function is shown on the right here. And what this does is it's a really simple function. It's just a linear function, except wherever the input is below 0, it caps it to 0. So it's max of 0 and the input y. And this really simple nonlinearity allows you to basically take your filtered output and then select out only certain aspects of it, the ones that are above 0. And now we have linear followed by nonlinear. So we have a nonlinear computation. And once you start stacking these up, now you actually do get increasing representational power because it's no longer just a stack of linear operations. OK. So people have explored a lot of different possible pointwise nonlinearities. Tan-H functions, maybe you've heard of sigmoid functions. But it turns out that these ReLUs are really simple, really fast, and easy to work with. So that's the currently popular kind. OK. So now the third basic computational unit in these networks is a pooling operation. So what this unit does is you take your representation after passing through the nonlinearity, and then you want to aggregate the information in some fashion. And one popular kind is max pooling. That just says for every output node in the final layer Z there, you just take the max over some local set of inputs. Okay, so it's a really simple operation, and this set of operations here is the basic kind of computational unit that's going to be repeated over and over again to make really powerful algorithms. But I want to give you first an intuition for what this process can do. So imagine that you have some edge in an image, and you want to achieve invariance. You want to be able to, because maybe the world has the property that all you care about is that there is an edge, and that will tell you if there is an object, but you don't actually care what orientation the edge is at. So how can you achieve some non-trivial computation with this kind of network? What happens is you take that input, you pass it through this bank of filters. That's the weighted averaging, the first step, the filtering step. And these filters respond to edges at different orientations. So these filters are sifting through the input and selectively responding to parts that might be interesting, so edges. But now you want invariance. So this created this entire set of responses, but you actually want to respond equally and in a like fashion for any type of edge, if your goal is to just say, is there an edge at this location, since that might be semantically meaningful. So then you add this pooling stage, just as we saw before, and the pooling stage, if it's a max pooling operation, will just say, if any orientation of edge exists, if any of those filters fired, then we will get a high score, because we just take the max, we take the very best one. And this means there's a large response for any edge, regardless of orientation, and this is kind of the intuition for how these networks, through filtering and then pooling, can build up invariance to different structural properties in the world. Okay, so just to make it really clear, I only was showing some of the arrows, but a real network would have a whole bunch more arrows. You'd have the representation that every mid-layer node would be connected to a whole bunch of input. These are hidden layers that are getting some representation, and then you'd pool. Every single output node would pool over some subset of the inputs, and so forth. And this kind of unit here is the kind of basic computational building block of a deep neural net. Okay, so let's see what these nets actually look like. And it's just really simple. It's just you take the input, you filter, you pass through the nonlinearity to get yourself away from just having purely linear operations, and you do some pooling operation to maybe build up some invariance, and then you repeat. And every time you repeat, you're building up more invariance, more abstraction. You're getting farther and farther away from just the pixels. And eventually, at the end, you add just some kind of mapping, some kind of classifier that will map you back to some label space, some target label space. OK, so this is a convolutional neural net, feed-forward, discriminative architecture. And this basic kind of computation is showing up in so many different systems right now, so many different popular state-of-the-art systems, but it's really simple. Okay, and it can be written just as a composition of a lot of little functions, which are all alike. Just fx, where x is the input image, is the composition of the first layer of operations, followed by the same operations with different weights on the second layer, on and on and on, through this neural network, and then you get, at the end, clownfish. Okay, so before we talk about how you actually learn this is just describing how the network performs some computation. But the whole point of these networks is that you have to teach it what kind of computation it should be performing. So we have to actually learn these. But before we do that, let's see how we actually map it finally back to clownfish. How did we come up with that label? So what you have to do here is you have to take your final nodes in the network, these final neurons at the very output, and you have to somehow assign some meaning to them in order to map them onto a real problem. So suppose the last layer is a vector of neurons, and they have fired with some level of activity because they've received all their inputs, they've added them all up, and they got some activation. So this is the last layer of activation. Maybe clownfish has really strong activation and grizzly bear has really low activation. But what I'm showing here is that you can assign names to these nodes. I mean, this is going to be specified during the learning process. And then if you just take the neuron with the maximum degree of activation after all of this filtering, pooling process, that's a way of mapping it onto some semantics. And the network will say, OK, clownfish. Okay, and we'll be coming back to this in the learning, where I'll really be talking about how that happens. Okay, so the basic ingredients, just to summarize, are you have a set of filters that are going to select important features of the data. The common ones these days are linear filters and pointwise nonlinearities. And then you have a set of pooling operations that group all features that indicate the same thing. And you just repeat this over and over again to achieve kind of greater abstraction. OK, so this is how the neural network does its computation. How do we actually teach it to do that kind of computation? Because that was just taking some fixed network. But now we want to be able to adjust the weights to solve a problem of interest. OK, so how do we do learning? Well, just like I said before, the difference between this architecture and old ones is that we're going to be learning from end to end, from the input operations through the mid-layer representations all the way to the output operation. And what is going to be learned is the arrows. And remember that the arrows are the weights in the filters. Okay, so we had the filtering operation takes a weighted combination of the previous layer, and we have to learn those weights because those weights are going to tell us what kind of computation is being done. We're not going to be learning how many nodes there are. We're not going to be learning how many layers there are. We're not going to be learning the pointwise nonlinearity. All we're learning is the linear filter weights indicated by the arrows. OK, so how do we actually learn those weights? How do we adjust them? How do we fiddle them in order to solve a problem? OK, so the basic setup is like this. You have an input image, and we're going to be working in the framework of supervised learning. This means you are going to have a set of images and labels, where the label is given by some human, some annotator, who tells you what this should be called, and then the network will figure out how to adjust those weights, those arrows, in order to predict the right label. OK, so we take that input image, and we pass it through this entire network. And at the end, we want to check, did the representation that comes out at the end actually correctly activate the unit that we're going to call the clownfish unit? And if it did, we'll say that's great. And if it didn't, we'll give that a penalty. So the function that penalizes this, it tries to say, are you right or wrong, is called a loss function. So you're just going to be comparing the network to the ground truth through this loss function. And you're going to be trying to adjust the weights in the network to minimize the loss. OK, so the learning process can be expressed very simply as just trying to find weights of the network that will minimize this loss function, which is, of course, a function of the weights in the network. OK, so what does that loss function look like? So let's go back to our example of this output representation being a set of activations that correspond to different semantic categories. And what we want to say is that if the ground truth label for an image is clownfish, and the network output had high activation on the node that represents clownfish, then we want to say the loss is small. That was a correct answer. Whereas the loss would be large if the ground truth is grizzly bear and the network output is clownfish, because that'd be incorrect. So one really simple way of encoding this is what you can do is you can represent the ground truth label with what's called a one-hot coding vector, which just says the ground truth label, if it's grizzly bear will index into a particular entry into this vector. And what we want to do is we want to look at the difference between the estimated vector of responses, which said clownfish was activated a lot, so I'm writing that as z hat, and then the ground truth vector, which said, well, the ground truth vector just is one node is on, grizzly bear is on, because we know it's a grizzly bear. This is a correct answer provided by humans, and all the other ones are turned off. So we want to see the difference between these two vectors. This is just a way of making it concrete what it means to check if your output class is the same as your predicted class. Your ground truth class is the same as your predicted class. Yeah?
So in this case, like a dolphin or an angelfish is closer to a clownfish than a grizzly bear, right?
Right. So there's not really any for this type of loss, there's not any notion of closeness between categories. You can define different losses that would have that notion, but for this one, which is just a kind of categorical classification, that notion doesn't exist. Yeah. Okay, so now we can mathematically define a loss or a difference between the output representation and the target representation. And the common one for this kind of categorical, this multinomial classification problem is the cross-entropy loss. And what that says is you're just going to, these are two vectors, you treat them as probability distributions. So you treat the network output as a probability distribution over the possible things that are in the image. And it says, I think with high probability, it's a clownfish. And the ground truth says, I know with perfect probability, it's a grizzly bear. I have 100% probability over grizzly bear. And then the cross-entropy loss is just looking at the cross-entropy, which is a measure of the difference between these two distributions. And this loss will be minimized when you actually output grizzly bear if the thing is a grizzly bear, and you actually output clownfish if the thing is a clownfish. Okay, so the bigger picture idea here is that you have to, for whatever problem you have, define some kind of penalty for how different your predicted representation or predicted output is from the ground truth representation or ground truth output. So just as an example of a slightly different task, suppose our task is not to say recognize the object in the image, but instead it's to look at a picture of a door and respond how many newtons of force I should apply to this door to open it. Well, seems like a very different problem, but actually you can use almost the same network to solve this problem. Just change this final way of calculating the difference between a correct answer and a predicted answer. So this loss function is all you need to change. And all you have to do here is say, well, this is a regression problem. You're trying to predict a number. You're trying to predict how much force I should apply, given an input image in. You're trying to predict a number, how many newtons of force I should apply. So now you want the network at the end to produce a single number. So we just decide that the network should map entirely down to sort of a vector, a single neuron. And we just assign that neuron the semantics of a number of newtons that are predicted that need to be used to open the door. So maybe it predicts 100 newtons, and the ground truth is just another number, which is 10 newtons. So if this is a robot, it would probably break that door. And then we define our loss, our way of measuring the difference between the predicted output and the actual ground truth, using the simplest one for a regression might be a Euclidean loss, just what is the distance between the prediction and the ground truth. So when you're practically designing networks for a new problem, a lot of the work and a lot of the actual game is in determining what is the right loss for telling you if you're correct or not correct. And once you've defined that loss, now you can apply very generic machinery to try to learn weights that will minimize that loss. So this is going to look like the following. First, the network will see an example of a picture of a clownfish. A clownfish, it will try to predict an output. It'll compute how right or wrong it is with the loss function, and it'll get a score. Okay, then it will see another image, another label. It will try to predict if this is a grizzly bear or not, and we'll compute how right or wrong it is, and it'll get a score. Okay, now we'll get another one, a chameleon. Same thing again, and we'll do this for thousands of images. These networks usually take a lot of data to learn. And what I'm showing here, this equation is the loss for every example. So little l is going to say, if we predicted, if the ground truth, which is denoted as z, is chameleon, and our network denoted as f, given the image and a set of weights, predicted grizzly bear, that number would be high. But if it predicts chameleon, that number would be low. So this is just a kind of very standard machine learning framework of minimizing a loss function. And the learning objective can be written as follows. We're just going to try to find weights that will be correct for as many example training images as possible. So we have some set of training images, this chameleon, this grizzly bear, and so forth with labels. And the goal is to make sure that for as many of them as possible, taking a sum over all of those training examples, we got the right label, or we minimized that loss. OK. So how are we going to do this? Well, people have thought of all kinds of crazy algorithms. If you listened to a tutorial on this a couple of years ago, you probably would have heard of greedy pre-training and contrastive divergence and all kinds of crazy things. But nowadays, it's really simple. It's just gradient descent. So this is the best time to be learning the material because it's really simple. OK, so we take that function. I'm just writing it as L now, big L, so that I'm not explicitly summing over all of the training examples. But we're just going to be trying to minimize the entire loss on some training set of images. And the way gradient descent works is, if you're not familiar, it's really simple. You just take your loss and you try to minimize it. You take some function, you try to minimize it by walking in the direction of steepest descent, just descending the gradient of the function. And as you walk in the direction of steepest descent, you will tend to end up at a minimum, a local minimum. OK, so the weights on one iteration of the learning algorithm will be at some state wt. So at time t, they'll be at wt. And then we just take a step in the direction of the gradient of the loss function with respect to the weights. So we say, which direction should I fiddle my weights in order to do better at correctly classifying all of these chameleons and grizzly bears and so forth. And that eta t parameter is what's known as the learning rate. This tells us how big the steps are. And this is one of the kind of important parameters in deep learning algorithms. You have to decide, should I take little steps and be very careful, or should I take big steps and get to the solution fast, but maybe overstep the solution? So to give you a kind of a visual intuition of what this might look like, suppose that we have a loss function L over two different weights in the network. We're just going to be tuning two different weights, and we want to see how can we tune those weights to get a low, to be very correct, meaning have a low loss. And so higher peaks mean we're doing worse. And you see that there's an optimum over here. And if you do gradient descent, you'll just gradually be walking down the slope, just like a skier. But you actually might get stuck in this little valley in the middle. In order to make sure that you don't get stuck too easily, and also to just have a more efficient algorithm, people actually do stochastic gradient descent, where you're not going to be descending in the direction of steepest descent, but you're going to be kind of jumping back and forth in a semi-random fashion. And this helps you to pop out of local minima and find a better solution to the minimization problem. OK, so yeah. Oh, question? Yeah.
So when you said there are these other algorithms, contrastive divergence and so on, so they're not using that anymore. What is the reason that they?
So I think the reason is that this is just simpler, really easy to implement, really fast, and it just works as well. And the other things, they possibly could work better, but there's been a recent trend of kind of taking a lot of the tricks and realizing, oh, big data and big GPUs mean we don't have to bother with that. Okay. So these techniques might come back eventually. They might be smart techniques. But I think we're at a phase of the cycle where things are becoming simpler because we could get away with it.
Just because there's more computation.
Yeah, yeah. Speed, computation, yeah. Uh-huh.
Sorry, just a question. So the backpropagation, wasn't that a long time ago? That was just gradient descent, right? So then
yeah.
you moved away from it and then came back to it?
No, so this is, OK. I'll talk about backpropagation now. And this gradient descent operation can be implemented efficiently using this backpropagation algorithm that you guys have probably heard about. So this is no different than backpropagation. The basic idea is that we're doing gradient descent, but you have to compute the gradients of a really big network, a ton of parameters, millions of parameters, and you want to compute a gradient with respect to them. So this is a difficult computational problem, but it actually unrolls quite nicely because the loss function is actually just the concatenation of a lot of functions. Because remember, the network is this concatenation of a lot of simple functions, linear, nonlinear, pool, linear, nonlinear, pool. So you can write that out as just f1 of f2 of f3 of f4 of f5 and so forth. And the way that you can then take a gradient of these types of functions, which is compositions of many functions, is with the chain rule. So this is just a simple rule from calculus that tells us how to decompose the gradient of the entire composition of functions into gradients of each part. And backpropagation is a name for an efficient algorithm for computing gradients in this setting. So it's really, backpropagation is just a way of computing the gradient, and then you can do gradient descent once you've computed the gradient. Okay, and the basic idea of backpropagation is that first you are going to run the network forward with the current set of inputs. So you run each of the training image through the network, and you see what kind of errors they get. Now, the gradient with respect to the final layer, the loss layer, is going to be a function of the current loss. So you have to run the network forward to see what the current loss is, and then all of the gradients for how to update the weights, how to tune the weights earlier in the network are just going to be taking that final output and multiplying it by, incrementally, iteratively multiplying it by the gradient of each computational unit that comes before. And this can be implemented by intuitively running the network forward. It produces some errors, and then you send those errors, you communicate those errors backwards, and each time they get updated according to the kind of local gradient. Yeah, Max?
So if you use rectified linear units, it's no longer differentiable. Does it just not matter?
I think that people kind of ignore that. So actually, I'm curious about that myself, if anybody has an answer. But basically, these rectified linear units have this singularity, which is nonlinear. They're not differentiable at 0. But I think people find that doesn't actually affect things in practice. Yeah.
Don't they just like not differentiate? Just use like, a small, like, something over here minus something over here instead?
That might be right. Yeah. Yeah.
So like, instead of taking an actual symbolic derivative, I thought people just.
Right, so it's not a symbolic derivative. It's all numerical. It's all about just taking these error signals and propagating them back. And I think that you treat everything that's been either maxed out and zeroed out by either the max or the ReLU as just zero derivative, and the only error signals that get propagated back are the ones above 0. And then the nonlinearity, I think, just doesn't really show up because it's only something that would show up in an analytical solution. But I'm not sure how justified that is, and maybe we can talk about these details more later. Okay. And again, the basic intuition is you propagate these error signals back. This is just an efficient way of computing the gradient of the entire network. And to give you kind of a visual intuition, the networks are trained in the following fashion. First, you send the inputs through the network, you compute a loss, and then you propagate the error signals back, which is just a way of computing the gradient, which is just a way of telling you how to tune the weights, how to change the weights to minimize that loss. Okay, so this is really all there is, or the majority of what there is, to learning with convolutional neural nets and getting really good state-of-the-art performance. There's a couple details, like you might want to add some momentum to your updates, but these are more minor details. Okay, but one kind of important issue is, so I told you how to minimize the loss, how to make it so that you can get, let's say, a perfect answer for every training image. If you have enough parameters, you can always tune them around, enough weights, you can tune them until you have gotten the correct answer for every training image. But how do you avoid overfitting? So in the Bayesian lecture, you guys probably heard about likelihoods and priors. And you guys probably know from just using machine learning and regression systems that overfitting is a big problem. If right now we're only minimizing the likelihood. We're only trying to make the network give us the right response. But how do we make sure that it will actually work on held out data, some new data you've never seen before? And this is where the networks don't align very nicely with probability models. But there's a couple of ways that regularization or priors implicitly get into the networks. So I just want to tell you a few of those right now. Okay, so one is that the network architecture is a prior. 2 is that you can do something called data augmentation. And 3 is a technique called dropout. So let me tell you about each of these briefly. So one, the network architecture is a prior. Well, we don't actually have an infinite network. we don't have infinite weights that we can tune in order to fit the exact training data. For example, the fact that we're using convolutional nets means that we're enforcing a really strong constraint, which says that the semantics of the world, like the identity of something being a clownfish, are independent of where that clownfish appears within the spatial frame of the image. We're saying that there's some translational invariance property of the world, which happens to be true. If a clownfish swims to the right, it doesn't change into a new organism. It's still a clownfish. OK, so these types of choices are actually encoding pretty strong priors about how the world works. Another intuition about how the network architecture can encode some information, some prior, is that if you have a layer somewhere in the middle which only has a couple hundred nodes, let's say, that means that the entire information about the input image, which is probably like thousands of numbers, 256 pixels by 256 by 3 color channels, all that information about that image has to be represented in a few hundred numbers in some mid-layer representation. So because we're only using a few hundred numbers to represent that, this is enforcing some kind of parsimony. And this is penalizing complexity. So you have to learn simple rules for interpreting your data, and simple rules generalize better. OK, so if you guys have heard of autoencoders, this is essentially the way that they work. They pass information through a representational bottleneck, which makes you come up with a compact, parsimonious representation. OK, but that's kind of an aside. OK, so the network architecture actually encodes structure about the world. This is one important thing. Another way that people can avoid overfitting is, well, if you have infinite data, you don't actually have a problem with overfitting. Because if your data set includes every possible thing you could ever see, then you don't have to worry about generalization, because you just memorize everything that you could possibly see. So a really common trick is to try to get a little closer to that by increasing your data set with what's known as data augmentation. So data augmentation means rather than just showing grizzly bear and clownfish, you also say, well, I know that a flipped image should have the same label as the unflipped image. I know that a clownfish that has been flipped about the vertical axis, a mirror image of a clownfish is still a clownfish. So you're essentially, what you can do is you can encode this strong prior, which is that mirror images have the same semantics as the unmirrored image. And the way you can enforce that prior is you just give the system an example of the mirrored image and the unmirrored image, and additionally an example of a slightly translated image and a slightly scaled image and so forth. You can do all this jittering and wiggling of the input data in order to just say, network, this mirrored image is still a clownfish, or a tree here. This slightly translated up image is still a tree. OK, so this is kind of a hacky way of adding the prior that mirrored images and slightly translated images and slightly rotated images should all be the same thing. OK, and then one other way that you can avoid overfitting is a currently popular trick known as dropout, which is, well, if you have a standard neural network, it has a ton of these weights, like I was saying. But you can oftentimes do a lot of computation with far fewer weights. And one way of making sure that the network won't learn a really crystalline rule for exactly how those weights should be set just to match some objective is you can randomly cut wires on every other iteration. And what this does is it makes sure the network will learn a rule that's very robust to kind of brain damage, that's very robust to having little lesions come here and there. And this actually works really well in certain cases, gives you a little boost in performance at making the network generalize better because it's robust to, it just has learned rules that are simpler, essentially. It has learned rules that are not going to be damaged by having a few neurons in the input getting the wrong signal. If they get the wrong signal because it's some new test item you've never seen before, well, there's another set of neurons that will interpret it correctly. So dropout is kind of regularization as well that forces the network to learn simpler, more robust rules. And maybe there's some connection to how the brain is there's a lot of kind of everyday brain damage that our brains don't just like crash as soon as you cut some wires, unlike a computer where if they cut a couple of wires, it will crash. But these networks have that same property. They're very robust. Okay, so that's the overview of the basics of just how these networks work. I'm going to now talk a little bit about what they learn, but just to recap first, what we've seen is that these deep neural networks are just a hierarchy of simple repeated computations, linear filtering, pointwise nonlinearity, and a max pooling operation. This is the most common set of operations, although sometimes people add a few more. Two kind of intuitions are the filters sift through the data, find important features. The pooling builds up some kind of invariance by grouping alike features. And the entire thing can be learned effectively with vanilla stochastic gradient descent. And we're really lucky that at this moment, you can get away with something so simple. OK. So any questions so far? Yeah.
What is the rationale of pooling here? For, like you mentioned that sometimes people use maximum and probably sometimes it's average.
Right.
So I wonder, like, what's the rationale of pooling here?
So in fact, sometimes you can get rid of pooling entirely and just have convolution, ReLU, convolution, ReLU. And it can work as well on, there's a recent archive paper just out that shows that on some, I think, Pascal object detection. And people have also shown that you can replace max pooling with average pooling in certain cases. So I think that there's good reason there's a good intuition behind max pooling, like it's achieving a hard kind of invariance. But the other types of pooling, or even if you just get rid of pooling, a convolutional filter can act kind of like pooling. Like average pooling can be implemented as a convolution because it's just a weighted sum. So all these different varieties of pooling might be qualitatively actually not that different. And in practice, people have several times shown that one or the other can do as well. The theory of how all this works is still being developed. Yeah.
I mean, you talked about generating infinite data by rotating the images and stuff like
right.
that. And that's in some way similar to what max pooling is trying to do. So, I mean, having both of those, it's not clear that you get any equivalent benefit from both of those situations, right? Like if you're able to train your network to recognize
I see.
whether
Yeah.
it's rotated or not.
Yeah, that's interesting. So I guess if you have a bank of rotated filters, you could just replace that by having a single oriented filter and a bank of rotated images. Yeah, that's an interesting trade-off. You could probably I don't know if there's a good reason to do one or the other, really.
Maybe when the location is global or local, right?
Yeah, well, I guess one issue is global or local because the filters are just going to be small local things. And another issue would be data augmentation is still kind of the least efficient way of doing it because you'd really have to rotate all of your data. And if you encode it in the network architecture itself, then it kind of automatically tries rotating essentially it's trying to rotate every new piece of data, so it might be a more efficient way to do it. Yeah.
Just a historical question. So my understanding, which is extremely limited, is that some of the important advances that actually distinguish modern kind of implementations of neural networks from the implementations in the 70s was these choices of nonlinearities, choosing them to be these very simple.
Yeah, that's true.
As opposed to functions like sigmoids or tangents. Could you explain what was the actual insight and why things like this are supposedly speed up optimization a lot, or am I just completely delusional?
Yeah, so I think people were initially wary of ReLUs because they grow without bound, and they thought, oh, you need to have a tanh which will saturate. But that, for some reason I don't actually know myself, that didn't turn out to be a problem. So I think that the computations can be done faster with ReLUs. It's a very simple operation. I'm not entirely sure actually why ReLUs are more effective, but it is true empirically that they were part of the 2 or 3% boost that pushed these things into the media essentially. Does anybody know the answer?
I would argue that it's sort of like a dynamic range problem that you have with right? Like if the filters, the range of the filters is way outside the range of the nonlinearity in which you're operating, that's good, but maybe that's less of a problem.
I see, because they just go without bound, and there's no parameter for how tall they should be. Yeah, it could be.
The 10H still works pretty reasonably now. So.
I see. Yeah, I think one of the unfortunate things right now is that people will say, oh, max pooling isn't important, or it is important, or tanh or isn't. But then the next year somebody will say, oh yeah, but you just pick a different parameter and it works as well. And I guess what I take from that is that what matters more is having a cascade of simple repeated units that build up abstraction, and there's a wide class of models that are probably more or less equivalent in their power. Mm-hmm.
Do these kind of structural decisions have a large impact on what kind of filters you end up with?
Let's see. I think that for the first couple of layers, the filters almost always, and we'll see some examples, they almost always come out to be the same kind of thing, Gabors and kind of some simple wavelet basis. And there's not, as far as I know, a huge effect of the architectural choices. Later in the architecture, where it gets more abstracted, it probably has a bigger effect, but I don't really know. Yeah.
So something I always wanted to ask about is, so in case of perceptrons and like non-convolutional networks, there's the general function approximation theorem, right? And I wanted to ask if you know if it holds for CNNs, or if there is an extension of that for CNNs.
Saying that like a three-layer network can approximate any function, these kinds of findings. A finite layer network.
Can approximate anything, right?
Right.
I just don't know if it's extended with convolution, right? So it's convolutional weight sharing.
Yeah, I don't know actually, but I will say that these convolutional architectures almost always have fully connected layers at the top, which are, you can think of them as convolution with just a kernel which is the size of the entire domain, the size of the entire image. But they actually do at the very top layers have just a regular multi-layer perceptron with the same theoretical guarantees. That's a common setting. I'm not sure if the guarantees hold for just strictly the convolutional layers with local convolution. Yeah. Oh, sorry, actually, middle, yeah.
Is the number of layers and the size of each layer and all that, is that pretty much still art, picking those things? Or
yeah, I think, and we'll see a little bit about this, so I'm going to go into some practical usage pretty soon. But I think still these choices tend to be somebody happened upon a good set of number of layers and everybody else just follows that and doesn't try to change it. So there's one like AlexNet is now probably the most used network, and most people don't try modifying it. They just stick with that architecture, maybe change the loss function or one or two little things.
And the networks are symmetric across layers usually, or?
Symmetric.
As in every layer is the same as, is everything else?
Approximately the same. Oftentimes you'll leave a pooling layer out here and there. Maybe you will add some, I didn't mention it, but there can be normalization layers. So they're not entirely symmetric, but they're roughly stereotyped, repeated kind of computations. Yeah?
I also had a question I've always wanted to ask about about the hierarchies thing, sort of. Has anyone tried just like nearest neighbor or something on the just data sets the size of what people are training their networks on?
So people have tried various things like that, but actually the big disadvantage of nearest neighbors when you have millions of images is it's very slow. Nearest neighbors, to query a million images, you either have to make a big complicated data structure like a KD tree, or you just have to iterate through all million, but it's very hard to make those fast. Whereas these networks, the advantage,
I'm just wondering about this
just for performance.
Statistical properties of it.
The statistical properties. I don't know, George, do you know? Nearest neighbors often work surprisingly well. It often will. I know, for example, at image captioning, which is a currently popular problem, image in, caption out. People are doing deep learning on that. But you can also do a kind of nearest neighbors approach and beat a lot of the current methods. But that nearest neighbors approach actually has deep features in it. It is a complicated answer, but yeah, I think that it's still unknown. Yeah.
So I'm just curious, is there any way for working around the fact that gradient descent might not always converge at the global minimum?
To guarantee that it will converge?
Yeah. It might not always converge
Yeah.
at the global minimum.
So
is
it-
there any way of working around that?
So these things are not convex. They're not. It's not guaranteed to converge to a local minimum. It might just find to a global minimum. It might just find a local minimum. But what people have noticed is that most local minima are about as good as each other. So it turns out that the global minimum empirically tends not to be that much better than the local minima, or there's a very large set of local minima which are all kind of equivalently good, and this kind of justifies not worrying too much about global minimization, but that may be in the future something people want to work on that more. Yeah.
Just a very quick comment that I at some point found very enlightening about this.
Yeah.
Sort of stage, which is even if you have a series of linear, just if you remove the nonlinear steps, and you just are training a series of linear matrices.
Yeah.
The loss, and you use pretty much any loss function, your optimization problem is still nonlinear, because you actually take derivatives with respect to all the weight things. It's sort of like a polynomial degree equal to the number of linear maps you compose. This is just important to know.
Interesting.
If you think about what is a kind of a generic, maybe high degree polynomial like, and what is gradient descent on that, you get a lot of intuition versus I think some of the properties of how gradient descent works.
Interesting. Yeah. So I guess the entire thing will be linear, but the optimization is not.
Yeah. I mean, the actual, like, when you compute the gradient with respect to all the weights,
Yeah.
it's not linear.
Okay, so just for the sake of time, let me move on to the next section. These last two will be a bit quicker. So what do they learn? So I think this is a really exciting area of current work, which is to try to understand, because these things are kind of almost black boxes, right? We have some intuition for what's going on, but we really don't know what they've learned about the world. And if we want to know how vision works or how audition works, we really want to know the classical things, like does it represent surfaces? Does it detect parts? And so people have recently been trying to actually understand what are the representations that are learned and how does that explain the performance of the networks. This is very much ongoing. I want to point you guys to play around with this tool first. So there's a lot of work that people have been doing. Antonio Torralba is at MIT. He's one person who does a lot of this. And he has a tool where you can take a network that's been trained to take an image and predict a label of the scene category, like is it indoor or outdoor, is it a kitchen or a bathroom? And then you can take the entire network and you can click on nodes in the network and see the connectivity to other nodes. And you can also see kind of the receptive fields of the neurons. So these are all a lot of neurons, and you can click on this. It's like having a brain where you can just probe anything you want and see what it responds to. So it's a lot of fun to play with and give some intuition. So I'll just say that you guys should check it out. So we'll be posting these slides, and you can get the link there. Okay, so the first thing that we can do for just even very simple visualization is we can ask what kinds of filters, what do they look like on the first layer of the network? And this relates to one of the questions that was asked. Do they always learn the same filters, regardless of what you train on or what their architecture is? And the answer is very surprisingly often, this is what the filters on the first layer look like. It doesn't matter if I'm trying to classify images, I'm trying to process even sounds, if it's some kind of two-dimensional representation of sound. If I'm trying to detect pedestrians or I'm trying to predict surface normals of shapes, you tend to get a very generic kind of wavelet basis with all these gabors. And this relates back to people in neuroscience like Olhavson and Field, who said that bases like this, sets of filters like this, efficiently encode natural images, natural signals. And these networks always converge to a similar set of bases. I mean, you can really push it if you want, and that doesn't have to be true, but you will see very many papers with diagrams exactly like that one on the left. Another way of investigating what is learned is not to look at the filters, because after the first layer, it becomes very confusing to understand what the filters are doing. These filters on the first layer look like edge detectors, gabors, and so forth. But another way to do it is you just look at the patterns that most activate a given neuron. So this is kind of like spike-triggered averaging or spike-triggered like visualization. You're just saying whenever the neuron spikes, let's see what patch it spiked with respect to. So these are the patches that most strongly activate a filter on the first layer. So here's one filter that really likes yellow, and then another filter really likes edges of this kind, and so forth. And the kind of interesting thing that you can get out of visualizing structure like this is you can look at neurons on the second layer, and you'll see that the patterns that the second layer likes are a little bit more abstract than the patterns that the first layer likes. And if we go up to the patterns that the fifth layer likes, then we really see a lot of abstraction and specificity to semantics. So a single neuron on layer 5 of the network really likes dog faces. These dog faces actually have very different, fairly different colors, and there's a lot of invariance that's been built up. For example, in the bicycle, this bicycle wheel is translated up to the left, and this one's in the middle here, but it's learned some kind of translational invariance, and we can begin to understand this by visualizing what the node's like. And the basic finding, a lot of people have been looking at data like this, the basic finding is that as you move higher and higher up the network, you get more and more invariance to simple photometric transformations, translations, color changes, etc. And this matches our kind of intuition for that the networks are building of increasing abstraction so that at the end they can group all dogs together and label it as dog. But a big question comes up here, which is, well, did the network actually know all the structure of dog face, or did it really only know something extremely crude that happens to pick out dog faces? So it's a question of, is the network almost generative in the sense that it can really reproduce a dog? It really encoded all of the geometry of a dog, or is it just strictly discriminative, which is what it was trained for, just to separate dogs by identifying some giveaway feature which might not have anything to do with the color and geometry? And one way to start to understand how much information the network encodes about the actual geometry and visual structure is to try to directly invert the network by finding the stimulus, in this case the image, that maximizes the output of a particular class. So the goal here is you say, let's find the image I that will give us the highest score for some class C. So S sub C represents the network's probability of some class C. So this is a score for dog, let's say. And it will try to create an image that makes the network most happily say, this is a dog, this is a dog. And the way people do this is they say, well, you could just find an image that maximizes that, but it's actually going to be a very noisy image because the network doesn't necessarily know about the manifold of natural image structure. It kind of doesn't care about certain low-level aspects of images because there's no need to encode those in order to discriminate one image from the next. All images share those properties. So you add a little prior, but notice how simple the prior is. This prior is just saying that the image should be smooth. It's saying that, in fact, it's less than that. This prior is just saying that the image should not have pixel intensities that go to infinity. So we want to make sure that the intensities in the image stay within kind of a compact range. And then when you run this and you find the optimal images that stimulate that network, it knows, so now this way of visualizing is a much more pure way of looking at what the network has represented because you're really directly inverting the network with only the additional prior that you don't want pixels to go to infinity. And if you look up close, you can see Dalmatian has like Dalmatian pattern, and cup has, you can almost see a handle on some of the cups. Dumbbell, you can really see the geometry, and you can see it's learned invariance to rotation because I see dumbbells that are rotated at multiple angles. So the network actually knows a lot of geometric and photometric structure that you might not expect. You might think that it could just get away with ignoring, not actually explicitly encoding the shape of a dumbbell. And people have kind of gotten excited by this, and so they've tried to say, let's not just find the stimulus that most activates the dumbbell neuron. Let's look at every single neuron in the network and see which stimulus most activates it. So we can take, on the top left there, we're taking a neuron. We're taking, in fact, the entire layer representation after the first convolutional layer. So we run a set of convolutional filters over the image, and then that gives us a representation, which is this filtered image. And then we try to find an input image that produces the same set of filtered responses. So this is telling us how much information is lost as we move deeper and deeper in the network. And the interesting thing here is that we can move all the way up through conv1, conv2. These are the first layer of convolutions, the next layer of convolutions, all the way up through conv5. The fifth layer of convolution is really deep in the network. And still there's a lot of spatial structure. Still there's some color information. Still you see a monkey face. But as soon as you get to these ones up here, which are FC7 and FC8, these are fully connected layers. These are not convolutional. Once you get the fully connected layers, you start to lose spatial structure. you start to scramble up all the information. And so we see how the network has increasingly built up a more and more abstract representation the deeper you go. But we also see that very deep in the network, there still is spatial and kind of simple photometric structure retained. So these are all just kind of tantalizing bits of information that we can maybe use to better understand really what's going on. But of course, it's very much an ongoing process. You can also look at the kind of how the receptive fields grow in size as you go deeper and deeper in the network. So the first set of filters only see a little tiny bit of the monkey face. But as you move up, a single neuron or a single small set of neurons on the fifth layer of the network is actually seeing most of the image. OK, so the message here is that the deeper we go in the network, the more we build up some kind of abstraction, but we can go pretty deep and still have more information about visual structure than you might think. It's not like we immediately get into cognition where everything is abstract symbols and then the network is just playing with abstract symbols. It's really playing with pixels very, very far into the network. So another way that people have tried to look at what these networks are doing is by querying the types of invariances the network has learned. And another angle on this is to look at equivariance, which means if you translate the input, or if you transform the input, how does the output transform? It's equivariant if the output transforms in the same way as the input transforms. So invariance is when if I rotate the input, it produces the same response. Equivariance is if I rotate the input, it produces a rotated response. So what people have noticed in this line of work here is that if I take an input image shown on the top row, and I look at a visualization of what the first convolutional layer has represented or the second convolutional layer has represented. If I flip or rotate the input, it will flip and rotate the representation. So the first couple layers in the network seem to be equivariant rather than invariant. It seems to be the case that you are not actually achieving, as I mentioned before, rotation invariance through the pooling, but somehow you're keeping a lot of information about rotation several layers into the network, and the invariance builds up only gradually. But it does build up eventually. So in this paper, these guys looked at how, as you move up deeper into the network, at what point do you lose this equivariance and get invariance? Or at what point does rotating the input not rotate the representation? And the numbers here indicate that on the conv1, 54% of the neurons are invariant to horizontal flips. They don't change the response with respect to horizontal flip. But by the time you get to conv5, it's 99% don't change the response with respect to a horizontal flip. So again, the story is as we move up in the network, we get more and more abstraction, and we build up variance, but actually fairly slowly, surprisingly slowly. OK, so let's think a little bit more about what these networks are representing as we move up. And one interesting recent piece of work is, here we go. It's this finding that object detectors may kind of emerge naturally in deep networks in the intermediate layers. When the deep network is trained to take an image and label it with the scene category, like kitchen or beach, well, the kind of classical vision hierarchy, the kind of David Marrs idea was that, well, first you extract edges, and then you extract surfaces, and then you get parts, and then you get objects, and then you get a scene. And what this paper is suggesting is that the deep net actually does something quite similar. If I'm just training it to recognize beach, it seems to represent object-like, some neurons represent objects in the middle. So this visualization here is showing the receptive fields of different neurons at different layers of the network. So on an early layer, pool 1, the first layer, the first pooling layer, the neurons respond to colors and edges. On conv4, the fourth layer, they respond to kind of textural patterns. These are more complicated patterns. And by the time you get to the fifth layer, you're responding very selectively to what we might want to call an object, like a staircase or a boat. OK. And they actually can quantify this and show that what it's showing here is that this is the percent of these receptive fields that people on Mechanical Turk would identify as an object or a place or a surface as we move through the network. And what we're seeing is that as we go from up layers 1 through 2 through 3 through 4 and so forth, we increasingly get more and more object structure at the top, and less texture structure, and less just color structure, edge structure. Okay, so this is again supporting the hypothesis that the networks are actually doing what we've always thought vision is doing, which is this hierarchical processing in which you start with simple kind of units, modular units, and you start putting them all together. You start with edges and colors, you get segments and parts, objects, and then you get coil reef. So of course this is not a theoretical or a closed story, but I think it's kind of an exciting direction these networks are going. Okay. So to recap this section, we saw that these networks, they have this huge capacity to absorb data. And in the end, that allows them to learn something kind of like the classical visual hierarchy. Not exactly like it, and there's a lot of ongoing work to see how similar the representations are. We get increasing invariance as we go deeper, but we still retain a lot of low-level stuff, like spatial layout, even all the way up through the 5th layer of the network. So we're not getting invariance immediately. Okay. So question?
Yeah, I would ask a 2.5 question. What don't they learn?
What don't they learn?
Yeah.
Interesting.
So what type of tasks are difficult for these algorithms, right?
I see.
What do they fail?
So one interesting thing is these networks are basically doing amazingly well at a wide variety of tasks. So while they haven't solved everything, certainly, there aren't many cases where you can say something else is obviously better for just the automatic task of predicting some property of an image or a video or text. But there are some interesting failure cases. I think that I have, let me pull up this. Okay, so yeah, is it solved? Is it all done? Well, no, not really. So here's kind of an interesting case that people have been looking at. If you take an input image, that bus, and you add just some structured noise to it, you add some noise which has been adversarially optimized to confuse the network, then you can make the network label that bus as ostrich or as car or whatever you want, just by adding little very minor noise to this image. And of course, a human will look at the bus on the left and the bus on the right, say it's the same thing, but the network looks at the bus on the left and the bus on the right. The bus on the right has noise added to it, and the network gets confused. So the network seems to not really know about the manifold of natural images in the same way that a human does, because it's a little kind of overfit to images without noise, but humans don't get confused by this kind of noise. Yeah.
So in this test, were they just essentially applying those tailored noise masks on the images and then just checking the outputs, or were they
That's right.
retraining that with the noise inputs?
No, I don't think they were retraining. They were finding noise that they're optimizing over the noise image in order to produce a desired output.
Okay, so they weren't seeing how it was doing, like say if you were to put that ostrich noise in the school bus.
Right. If you retrain the network, it probably can learn to ignore that noise. Yeah. Yeah.
I guess the natural question is like, is the dimension of like at any point the dimension of the space of noisy images were screwed up, or like this tangent space, is it much higher than the dimension of the actual image manifold, or not? In the sense that
I think
if I go and
right.
I retrain, I decide I have a lot of computational power and I do this for every image in my pool, and I make now the network recognize every school bus as an ostrich. So I add in all these kind of failure mode images and I tell it, I retrain the network to label them correctly. Will it then continue to? Will there still be? Will there continue to be kind of easy to find noise vectors after you?
My guess is that the space of noise is much, much bigger than the space of natural images.
Right.
And so,
the question is the space of noise that is bad for the network much bigger?
my guess.
Or does it still remain large after sort of editing?
Yeah, I don't know. I think it probably remains large because the space of natural images is so much smaller than the space of images. Yeah.
Maybe human vision is also vulnerable to this,
Right.
right? We have
Right.
various visual really has, like, it just so happens that optimization process is so hard, so that we only see a few examples
Right.
of well-known visual illusions, but there may be a lot of these things.
So I guess a question, yeah, I think that's really interesting. The question is, like, we can't do the optimization on humans very easily because you'd have to have a human in the loop that looks at the illusion and responds, and that'd be very slow. This has to go through, many thousands of iterations. I think, well, I don't know how many iterations, but it has to go through a lot of iterations to find the right noise pattern. But maybe there does exist like a mechanical Turk way to do this, to optimize an illusion and inject some structured noise to make it look like something else. I'm not sure if that's really, it doesn't seem like it'd be easy with this kind of noise. Yeah.
So the question is, if you choose an arbitrary noise, not something that's optimized, how
Right.
likely is it to compute?
Yeah, that's a good question. I don't know. I think it's important that you optimize it, which is why people have criticized this as it's kind of unnatural. It tells us something interesting about the network, but it might not be something that matters because it's been optimized. Okay, so there's a lot of, definitely it's not solved. Definitely there's more interesting things to do, which is good for us. Okay, so finally I wanted to give you guys some practical tools, and then we can move into the exercises, and then we'll be here to help you on those as we go. But just quickly, so there's a lot of architectures and frameworks for learning deep nets right now. A lot of really nice, robust code, a lot of mature projects. This was not the case 2 or 3 years ago. This is now the case. So it's a good time to get into this. And they're not actually very different than what existed in 1989. So I think this is actually a diagram maybe from 1998. But anyway, the basic idea of this network was 1989. 2012, same basic thing. Okay, it's just all of these things are just simple computational units just hooked up in slightly different manners. Here's 2014, where Google came and said, well, we can make a much deeper one because we have a lot of power. But again, it's the same thing. It's just you got some convolutional filters and pooling, simple operations, change one after the other. And these days, what you can do is you can basically just try these out on your problem with block programming. Basically, all you have to do is let's say I want to try a small network that does logistic regression. Well, okay, in that case, I can write in a coding environment that I want a network with 3 layers that have these properties. And now maybe that's not powerful enough. I can just go back to that coding environment, add a couple more scripting lines that say, no, I actually want 5 layers. And you can actually, in most of these languages, which we'll be mentioning in a second, you can define any directed acyclical graph of computational units. It's really just like taking little computational blocks and trying different architectures for hooking them up. And then to learn these things, you learn the arrows. So you just apply SGD in the same way to all of them, and it works quite well. So it can be a lot of fun to play with. It's kind of a black art for how to design exactly which series of computations you want. But people, as I was saying, they usually just kind of find one that worked last year and go with that, and every once in a while try a new detail. So there's a lot of different frameworks for this. Probably maybe the most popular is Caffe right now. It's very fast, mature. It's relatively hard to use, I think, pretty hard to install. So we're not going to be using it today. It's C++ with limited interfaces in MATLAB and Python. But if you want to actually be coding new loss functions, then you need to get your hands onto the C++. Another one is Theano. It's got a couple nice properties. It's got symbolic computation and automatic differentiation. So you don't actually have to now think too hard about your gradients in the backprop. You can just say, automatically do it for me, and it will handle it. And it's in Python. This Torch, this is what they use at Facebook. This is Jan LeCun's favorite one. And he's the guy who's famous for inventing convolutional neural nets. It's in Lua, which is kind of a scripting language. And then the one that we're going to look at in the exercises is MatConvNet. This, I think, is really nice because it's pretty easy to install, and it's really easy to use. It's just raw MATLAB, very limited compiled code. And the only disadvantage that I've seen so far, it's a little less flexible and a little bit slower than some of the other alternatives. But for a lot of problems, it can be good. Okay, when you're using these, there's kind of 3 levels of usage that people try. The first is if you don't want to do too much work, you don't want to spend weeks training something on a server, you can just use a pre-trained network, a pre-trained convolutional network, and just use it as a feature extractor. So I'll tell you in more detail what that means. The second level is you can take that pre-trained thing and you can adapt it with fine-tuning it to a new problem. And the last is you can train from scratch, but for this you probably need a big data set and a lot of computational power. Okay, so if you just want to use the features, what you can do is you can take a pre-trained architecture like AlexNet. This is an image recognition architecture. And you just put an image through it. And if you want a generically useful representation of that image, you just peel off the activations at the final layer, or maybe a couple layers back. And this method, if you just take that representation and do whatever you want with it, maybe you use that, you put a linear classifier on top of that representation for whatever target problem you have, it will work really well much of the time. And one basic kind of rule of thumb is that the deeper you go in the network, usually the better the representation is for generic high-level tasks. But if you want kind of a lower-level task, like you actually want to do edge detection, then you might want to not go to the very end of the network where everything is abstracted, but you might want to peel off the representation at an intermediate layer. Okay, and if you want to go one step beyond just peeling off a representation and using it as a generically useful representation, you can fine-tune your network. And this is really simple as well. It just involves 3 steps. You download the pre-trained network. You replace the final loss layer with a new target loss for your specific problem. Like, let's say you have a network trained to do image recognition, but you want to do predict. You want to do video processing. Then you'll have to maybe adapt the inputs and the outputs of your problem a little bit, but you can otherwise just use the pre-trained weights in between. And you just run your stochastic gradient descent on your slightly adapted problem, and it will take this good initial solution and adapt it very slightly to your new problem. Okay, and of course then you can train from scratch, but let's see, how much data do you actually need if you're going to try to train from scratch? Because of course you want to train from scratch to do really well and have a really clean solution, but the state-of-the-art methods have been trained on millions of images. That's not so much fun to work with. Kind of interesting thing is that recently people have been showing that you can get decent results with far fewer images. In fact, even with just 10K images, you can do decently well. So you may think, oh, deep learning is only good for millions of images or millions of labeled examples, but actually you can do decently well with fewer. Yep.
What's
the gap?
Insight?
Oh, the insight?
Yeah. Some people tried this before that paper, right?
I think that so there is a gap, and people who want to compete on numbers will not like that gap, but it depends on what your task is, what your goal is. And yeah, I don't know if there's actually much of an insight beyond that. You lose some performance, but you can do decently well. And lastly, if you're thinking, oh, I need a lot of labeled examples, even 10K is too much. Well, with unlabeled data, in a kind of unsupervised mode, in a sense, you can often do almost as well as with these fully directly supervised methods. And these methods work by just trying to, for example, predict. They try to train a network that will just predict some aspect of the data from some other aspect of the data, like predict which images appear next to each other in a movie, so that the labels are just temporal adjacency. Okay, so if you're worried about data, there's actually some ways around that. But you do need some hardware. For a lot of problems, you can run these things on a CPU, that's no problem. You can't train them very quickly on a CPU unless you have a small network. But for a lot of problems, that's sufficient. So don't worry if you don't have a GPU, you can actually already be using these. For big problems, you do want a GPU, but you don't actually need anything more than a single powerful GPU. Most state-of-the-art methods that are using deep learning are only really trained on a single GPU because people haven't even engineered good tools for parallelizing across multiple GPUs. And you can use GPUs on OpenMind, and this is the department's server system for any BCS people to use. Okay, so finally, let's look at a couple fun things really quickly that you can do just to say that it's not only image recognition that I've been talking about. Well, we can get a dense set of labels. We can understand more about an image than just a single label. You can model things like perception. Let's say you want to know where people look in an image. You want to model eye fixations. Well, this is a really complicated saliency modeling problem, but deep nets now are the best things at fitting the human data, at telling us where people are going to look in an image. You can also model brain activity. So Jim DiCarlo and other people have been working on this, showing that these networks learn representations that are quite similar to what's going on in the brain, and this gives us a tool for perhaps understanding something actually about the brain. And of course, you can do fun things like beat people at playing Atari games. So basically, whatever problem that you're interested in, there's probably some way of adapting it into a deep learning framework. It won't necessarily solve everything, but I still think there's a lot of low-hanging fruit in this field. Okay, so the take-homes for practical use are, well, this is slow to learn, but very fast at inference time. So you can run it on a CPU at inference time, but you probably want a GPU to learn these things. They require a lot of data, but you can avoid this by using a pre-trained network. And sometimes you can get away with not much data for only a minor performance loss. They achieve great performance, and there's many easy-to-use implementations. Okay, thanks.